Hi everyone. As we continue our study of matter, we once again find ourselves checking out our matter flowchart. So you hopefully can start to see that this is a really valuable resource for you to use. We've already talked about pure substances over here on the left-hand side. We've already talked about different types of mixtures, and now we're going to take that study a little bit deeper. We're going to be living down in this lower third down here on the right-hand side. We'll be distinguishing between solutions, colloids, and suspensions today. So let's give that a look. When we think about these three, the easiest way to first kind of draw a dividing line is between things that are homogeneous and things that are heterogeneous. So solutions are homogeneous, suspensions and colloids are both heterogeneous. We're going to take a look at solutions first. When we look at solutions, a great example of this is coffee. And I know Folgers is good to the last drop, and that's a really good slogan to use here because for our purposes, let's assume that that coffee tastes the exact same for the first sip as it does for the last sip. So this thing is completely indistinguishable. When we look at that solution, there are going to be two parts of it that we look at. So one is called the solute, one is called the solvent. The solute is the thing that is getting dissolved. Typically there's less of it, and it's the thing that we want to kind of break down and make go away and disappear, if you will, into the thing that's dissolving it. Now, obviously it doesn't really disappear chemically or physically, but it might look like it goes away. So for instance, if you dissolve salt in water, that salt doesn't look like a solid anymore. It's kind of mixed in with that liquid. So the solute is that thing that's being dissolved. Conversely, the solvent is the thing that does the dissolving. So if we had an example, if we had sugar in a glass of water, the sugar is the thing that gets dissolved, so we call that the solute, whereas the water is the thing that's doing the dissolving, so we're going to call that the solvent. One of the ways that we're going to distinguish between solutions, colloids, and suspensions is by their particle size. So you'll notice for solutions, the particles range from about 0.1 to 1 nanometer in terms of their diameter. So remember, diameter, if we're looking at the particle, this is the distance across that particle. Now, you have a table in your note guide that's really useful to see if you can look at comparisons of these different types of particles. Particle size is a really important one as we distinguish between solutions, colloids, and suspensions. Now, before we talk about the other two, let's think about what exactly a nanometer is. So here's a table that shows you different things and their diameters in nanometers. So human hair, that has a diameter of about 100,000 nanometers. DNA, 2.5 nanometers. We know that these are really, really darn small things. So let's back up again. We said that solutions have a particle size of 0.01 to 1 nanometer. So that's about 1/100,000th of a human hair. So we're talking about things that are really, really darn small here. One of the confusing things about solute and solvent interactions is that we're used to dissolving solids in liquids. So for instance, we often think of dissolving something like sugar or let's say table salt. That would be our solute. In something like water, H2O, that would be our solvent. And we're used to that. We see that. We've maybe been to the ocean. We know that that's salt water, so it has salt dissolved in water. But it turns out that we can actually dissolve different states of matter in themselves or other states of matter. So for instance, we would make something like the air around us, we would call that a gaseous solution because we actually have different gases dissolved in one another and they're kind of randomly dispersed throughout in this mixture. So that's a gas being dissolved in a gas. We can also make a mixture of metals or solids. We call that an alloy. We'll actually have an opportunity to make this alloy called brass in lab a little bit later on. So we'll be doing that. But it doesn't mean for a solution that we always have to have a solid in a liquid. Here's some other types of solutions. So here is a liquid being dissolved in a liquid. These little green molecules over here on the left-hand side, this is hard to read, but it says C2H5OH. So that's an ethanol molecule. Those are being dissolved in the H2O water molecules. That's a liquid being dissolved in a liquid. Here we have copper 2 chloride, CuCl2, being dissolved in water. This is a solid being dissolved in a liquid. So another type of solid-solute interaction. This one here on the right is one we're probably a little bit more used to because it's a solid being dissolved in water. But this is just to illustrate that you can have different types of solutions formed from different states of matter. So here's a cool table that you have that shows all of these different states of solute, states of the solvent, and then the resulting state of the solution. And you'll notice that they're not always the same, right? So if you put a gas in a gas, chances are it's going to make a gas. That makes sense. But if we jump down to the next one, if we put a gas in a liquid, oftentimes that makes a liquid. So CO2 in water, this is like carbonated, like Coke has a lot of CO2 in water. So this is a cool place to look to see how different solutes and solvents can make different types of solutions, and it doesn't always depend on state of matter. In other words, we can use a lot of different states of matter to make different solutions. Let's change gears now. Let's talk about heterogeneous mixtures. So those solutions we just discussed, those are all made out of really, really small particles, and they look the same throughout. But if we think about stuff that looks different throughout, if you look at the soil in this picture, you can see little bits of bark, you can see little bits of sand or dirt or other things. You can visibly distinguish different parts of that mixture. So that's why we call it heterogeneous. There are two types of heterogeneous mixtures that we're going to talk about. They are called suspensions and colloids. And again, one of the big ways we're going to distinguish these is to think of particle size. So let's talk about suspensions first. This isn't when you get sent to the principal's office. Let's please try to avoid that. But if we're thinking of suspensions, we are talking about particle size greater than 1,000 nanometers. Remember, solutions were 1 nanometer or less. These are 1,000 nanometers, so way bigger in terms of the particles. And it turns out that these particles are so big that we can separate them out by using something called a filter or filter paper. The other thing that's cool about a suspension is that if you allow it to sit for a while, the particles are so big that they'll actually settle to the bottom. So here is something that is considered a suspension, and it looks like chocolate milk. But if you let chocolate milk sit around for 5 minutes, it doesn't do this. Right? In fact, it would be really bad if it did. You'd think, man, that chocolate milk has gone bad. I better not drink that. So this is an example of a suspension, and how we know that is you can see all of these particles have all settled down towards the bottom. And so a really good way to identify that you're dealing with a suspension is that the particles will eventually settle out towards the bottom. Again, we're going to be seeing examples of this actually happening in class, so sit tight for that. Colloids are kind of the happy medium. So we've got a three little bears situation. We've got solutions that are really small, suspensions that are really big, and maybe colloids are just right. They're somewhere in the middle. So these fill the range between 1 nanometer and 1,000 nanometer. And this gives rise to some really interesting characteristics for these things called colloids. Again, we're going to see different examples of colloids in class, but a really good example is foam. So we'll be dealing with shaving cream in a foam nature in class, and we'll be looking at some really interesting and crazy things that it does. So first off, here are some examples of different types of colloids that you may be aware of or you might have used in everyday life. So like I said, we'll be using shaving cream in class. Butter is a form of a colloid. Smoke we often think of as a colloid. This one is a solid being dispersed in gas. We're going to talk in class about fog and what's going on there. When you look at colloids, they do some interesting things. So one of the things that we're going to study with colloids is an effect called the Tyndall effect. And this is a little strange in this video because you can't see it in action, but we will see this in class. For right now, we want to know that Tyndall effect is very analogous with scattering light. So what does this mean? It means if you shine light, as we see in this picture here, if we shine light at a colloid, then it's going to scatter out those particles. So this beaker or glassware on the right, this is an example of a solution. The one on the left, this is our colloid. And you can see that the light is able to pass right through the solution, no problem. But as soon as it hits this colloid, it's kind of hitting a wall here, right? It's not going through like we saw before. So what's going on there is that these light particles, as they come through, are being scattered off in all of these different directions like this. A few are getting through, but they're being scattered every which way whenever they hit that colloid because they're running into the particles. So this Tyndall effect, this is what we call scattering light. And again, we're going to take a look at this back in class. You have a table that looks like this. It's a nice approximation of different solutions, different colloids, different suspensions. Remember, we said that particle size is a really important way to distinguish between these. Homogeneous and heterogeneous is another good way to distinguish. So thinking about these different properties in the table are good ways for us to kind of sift our way through that flow chart that we've seen many times and figure out what type of substance we're talking about. Let's talk briefly again about those solutes. Again, something we're going to see in class, but to round out this video, we're going to think about things that are electrolytes versus things that are non-electrolytes. You may want to think about places where you've seen the word electrolyte in your own, everyday life. I'll show you some examples of electrolytes in class. Briefly, electrolytes are things that, in general, they are going to conduct electric current or conduct electricity. So it turns out that everything that we know that is an ionic compounds are pretty much always electrolytes. And why is that? Because when they dissolve and their ions are then free to move from one place to another. So again, we'll go much more in depth in class. We have some demos to show you whenever we do this. But keyword, electrolyte, things that can conduct electricity, they can carry a charge from one place to another. Non-electrolytes can't do that. So if you dissolve something in water that can't conduct electricity, that can't carry a charge from one place to another, you call that a non-electrolyte. Molecular compounds, nonmetals and nonmetals bonded together, so molecules don't do this. Let's think of some really cool examples of this going on. So if we have a sucrose solution over here on the left-hand side, this is sugar. You'll notice this molecule, this sugar molecule over here on the left, when it dissolves, we separate one molecule, this one up here, from another molecule, this one down here, but both of those are completely neutral molecules. They don't have a charge. Something over here on the far right-hand side, like hydrochloric acid, when we dissolve that, the different ions separate completely. So hydrochloric acid is HCl. When HCl splits, you have H+, you have Cl-. The H+ actually joins a water molecule to make this thing, which we call H3O+. But H3O+, you'll notice, has a full-blown positive charge, and the chloride ion, Cl-1, has a full-blown negative charge, and those things can carry a charge from one place to another, which is why we see that light bulb being lit up here on the right-hand side. As I said, we're going to try this in class. We have an apparatus very similar to this, where we can actually turn on some electricity and see if we can conduct a current using different solutions. So sit tight for that coming a little later in class.